refrigeration cycles now. So as you notice the word here that we have different refrigeration cycles, and we will look at how they work and how can we draw the TS diagram for each refrigeration cycle. So most of the refrigeration cycles contain these elements here. So we have the compressor, and then we have the condenser. This is the condenser here. We have the thermal expansion valve here, and then you have the evaporator. For each of these components, for these components here, so you have the different refrigeration cycles, as well as there are some added components like the receiver here, and then you have the filter dryer here, etc. Okay, so let's now see how it works. So this is a device that is in our mechanical engineering laboratory. So this is a model of the refrigeration cycle. It is true for air conditioning systems, it is true for heat pumps or the refrigeration systems. All of them have the same components here, or a different form of these components. First one is the compressor, as I've said it. We have the compressor here. This is the outlet of the compressor. This outlet is, you know, that it is sent to this condenser here. This is the condenser. So then from this condenser, when it enters the refrigerant here, so inside this one you have the fluid, and this fluid, so it is called refrigerant. The fluid here, it is called and there are different types of the refrigerants. Okay, so the one famous one is that R134A, or you can have R22, etc. And then it enters to this condenser. When it leaves the compressor here, it is superheated. Okay. And then when it enters the condenser, it is again superheated state. And then when it leaves it here, at this stage, it will be that have a quality of 0. So it will be saturated liquid. Then it goes back to this receiver here. You can see that receiver. So this receiver is a tank. It is a steel tank, and that is used to store the refrigerant, because that in some time you can have that higher, that you can need higher refrigeration capacity, and it may be possible that you need a very minimum amount of the refrigeration capacity. So in these two extremes, you need a tank, okay, to that overcome these two extremes. And this tank is receiver. It is called receiver for the refrigeration systems. And then outlet of that receiver, you have the outlet here at lower part of it, because so here you have the liquid. It may be possible that the condenser, the outlet of that condenser, you have the vapor here, so that therefore top of it will be vapor. So you are trying to take always liquid, because this expansion valve should accept the liquid at its inlet. Okay, then it comes the filter and the dryer here. This is that filter, and this is cross-sectional view of the same device here. It filters, as the name says, and it dryers. Okay, so it dries. The dryer part is for the moisture, because this compressor here, it has some lubricant, lubrication system here. That lubricant or oil contains some water or moisture, or it is also possible the refrigerant itself has some moisture content. So this moisture content, or it is water, this or water or moisture content can freeze in some part of the tube system here. If it freezes, it will block it, and then you will have the damage to the system here. And this filter part, it is used to filter the particulates that are larger in size. Okay, that are larger in size, you are filtering it, and you are preventing it to move inside this tube system here. So at this part, you can see that the part here, this is called the desiccant. So this is not so simple as I'm saying it. There's filter and dryer, it has different components and a different, that reactions happening inside this system. This desiccant prevents the moisture, and then you have the screen here. You can see that screen, and you have different, that grill system here. And this grill system prevents the particulates that are trying to enter to this refrigeration system. Okay, then you have the side glass here. This is side glass. And by looking at this side glass, you can open it. You will see that there's a glass here. by looking at this glass here, you can see the amount of the vapor and the liquid. So you have to be sure that there is enough liquid. So this one should be liquid that enters to this the expansion valve here. The next component is that this expansion valve, thermal expansion valve here. It's also called the TXV, and then thermal expansion valve. Okay, and then the outlet of that thermal expansion valve, it will be mixture. So here you will have that mixture, and then from that thermal expansion valve you will have the condenser here. Let me just use a different color. Sorry, evaporator. You will have evaporator, and then from so this one is inlet for evaporator and this one is outlet, and you go back to this compressor here, to the initial state, and the compressor compresses again, and you have the cycle here. For the evaporator part of the heat pump or the refrigeration system here, it takes the Q in. It will need Q in because evaporation here, it is very similar to exactly the same as the boiler. Okay, so here you have the boiling process. The refrigerant change phase, and for this boiling process you will need some heat. That heat is Q in. For the condenser, it was superheated at the beginning and it becomes saturated, and therefore you will have that Q out. And for the compressor here, you will need work in, which is electricity, because you have to supply some electricity to rotate the compressor piston, or it can be that it is scroll type. You have to supply some electricity for that one. And you have this pressure switch. These are additional components to maintain the safe limits for the operation of this cycle here. So you have to have the minimum amount of the permissible pressure and the maximum amount of it. You have the manometer here and you have the manometer here. So you have two manometers to measure the outlet and the inlet of the compressor. Okay, these are the main components, and the thermal expansion valve. So I've shown the thermal expansion valve in a better view here. And for this thermal expansion valve, you can see this is the inlet and this is the outlet. And similarly here, this is the inlet and this is the outlet. Okay. And you have two pressures here. So that one pressure is, and as well as, so you can see that the bulb here, this is the bulb, and that bulb is also the same bulb here. You have the same bulb here. Okay. So for inside of this tube and the head system, you have the same refrigerant. So this that the bulb and the thermal expansion valve, it regulates the flow rate. How it regulates the flow rate? Say that the bulb here, you can see the bulb, this one here, you can have two ranges. Say that, let me write two extremes. So that first extreme is that very low temperature. So that very low temperature. And the next extreme is that you will have that very high temperature. If the temperature is very high here, so it means that inside the system here, the pressure will increase, because pressure is proportional to temperature. As the pressure increases, you will have the compression, so that the pressure will apply some force on this, that the component here. As it applies the force, it will compress the piston, that spring here. As it compresses the spring, you can see that this part, this outlet will open. Okay, this outlet will open, and you will have more refrigerant into the system. Okay. And the temperature is very high, you will have that more mass flow rate. So more m dot. And the opposite case is that where you have the low temperature here, you can see inside this one, you can see the tubing system here. So that inside this one, you will have the, due to low temperature, you will have the low pressure, and that low pressure, that you will have the opposite of the previous action. So this one will move up, and it will block the outlet of the condenser, and you will have that m dot less. You will have that less m dot. So why you have these two cases is that, so you have to be sure that you have enough amount of the cooling process, because this part is the Q in and it is cooling. Okay. If the temperature is very high here, so you need cooling. How do you supply the cooling? You supply cooling with more refrigerant. So you have the more refrigerant, and therefore due to the amount of the more refrigerant, you have the better cooling. And on the other extreme is that you have enough amount of the cooling so that you don't want any more. So what happens is that this one blocks that mass flow rate into the system, and therefore you will have that less mass flow rate. And it operates between these two extreme ranges. Okay. So this refrigeration system can be provided in two formats, which can be as a standalone and it can be as a split system. If it is standalone system, all of the components here, so that you can see the compressor, you can see condenser, evaporator, and the thermal expansion valve, all of them are in one device. So for example, this portable AC here, you can see this is portable air conditioner. So all components you will have in one device. Or it can be that window air conditioner system. So you can see again, all of the components are in one device. So this one is also standalone. This one is here also standalone. And it can also be in the split time refrigeration. And in split time refrigeration here, you will have two components. For example, here you may have that evaporator, and you can have that thermal expansion valve here. And on the outside unit, you will have the condenser and you will have the compressor. Okay. Two components in the outdoor unit. This one is outdoor unit. And this one is the indoor unit. In indoor unit, you will have the evaporator and the thermal expansion valve. And outdoor unit, you will have the compressor and the condenser. So this is split system. Or it may be that, for example, this is the central air conditioning system for laboratory here. For central air conditioning system, you can see the central outdoor unit. Here you have the condenser again and the compressor again. For the indoor unit, you may have the expansion valve and as well as the evaporator. Okay. Now let's start with the first refrigeration cycle here, which is the vapor compression refrigeration cycle. And for this one, we will have I will just write the components here. The first component will be compressor. So this one will be that, let me just write it, simple and ideal. The simple and ideal system. You have the compressor. Okay, inlet for the compressor, I will put a 1 here. Outlet for that compressor. This one is sent to the condenser here. And for that condenser, you will have that outlet as 3. And then you will have that thermal expansion valve and outlet as 4. And then from that thermal expansion valve, you will have the evaporator and the back to 1 here. So this is the main components of the vapor compression cycle, and I will analyze it in simple and ideal form. Okay, so let's start with the one value here. So that compressor, it works with vapor. So it means that the quality at 1, so therefore what you will have is that the quality at 1 should be 1. Okay, at the minimum case, it must be saturated vapor. It can be superheated vapor, but minimum case it should be saturated vapor. You have the temperature one, you have the pressure one. And after the compressor stage, you will have that P2, which is greater than P1, and of course T2, which is greater than T1, and this one is superheated. And then from the compressor, you have the condenser state. For the simple and ideal analysis, so what will I say? That you have that entropy 1, and here you will have that entropy 2, which is same as entropy 1. Okay, because the compressor is isentropic, reversible, and frictionless, and the adiabatic. So you have that pressure 3 here, so that pressure 3 will be same as pressure 2. Okay, this is the condenser, and for simple and ideal analysis, there is no pressure drop, and as well as you will have that X3 is 0, this saturated liquid. And then comes the thermal expansion valve here. For the thermal expansion valve, we have the P4, which is less than P3, and H4 is same as H3. This is the isentropic device. It is from the thermodynamic one. Okay. And then as well as you will have that H4 is same as H3, and you will have that S4 is greater than S3, and this one is irreversible. Okay, because if you remember from fluid mechanics course, is that you will have that KL coefficient. This KL coefficient, minor loss coefficient, is irreversible loss, and it creates the drop in pressure. But here I've written that thermal expansion valve, but any valve, or it can be that any flow restriction device is okay. So it can even be a pipe. Okay, it's okay. So at the end, it should, give me the pressure drop from P3 to P4. It doesn't matter if it is thermal expansion valve, it is plug, or it can be a throttling valve, or it can be the pipe itself. It doesn't matter. At the end, it should drop the pressure from P3 to P4. Now comes that P1 value here, and the P1 is same as P4. And for evaporator, this one is heat exchanger, this one is heat exchanger. And if I write the heat transfer, so here you will have that Q in, here you will have that Q out. Okay. These are the devices that I will have for this thermodynamic system. And now let's draw the TS diagram for this cycle here. I will draw all of the cycles for the R134A, so for this one, but different refrigerants will have different TS diagrams, but it will be similar in this shape. Okay, so I'll start with and as you can notice here is that you will have that P1 is same as P4, and the P2 is same as P3. Okay. P1 and the P4 is low pressure, P low, because it is inlet at the compressor, and this one is P high, because it is outlet of the compressor. Okay, now you have two pressure ranges, and for this system, I will take the low pressure as 140 and the high pressure as 720. So let me just say that P low is 140 kilopascal, and the P high is 720 kilopascal. So you have almost the pressure ratio is approximately here. It is, if I take 5, okay, 6, it is approximately less than 6. It is 5. Let's say that you have a pressure ratio about 5. Okay, now let's start with the compressor here. Inlet is quality as 1, and it is isentropic. So here you have the quality as 1 and isentropic to 720 kilopascal. This is state 2, and it will be in that direction. Then comes the condenser part. It drops the quality as 0. Right? It should be at constant pressure. You can see that the pressure line is constant here. Okay, it is state 3. And then from state 3 to drop into state 4 here, it is a thermal expansion valve, and the thermal expansion valve is isenthalpic device, but with an entropy increase and the pressure drop. And that the pressure drops P4 value, which is same as P1, and the minimum to low pressure value. So you'll have the drop in pressure, increase in entropy. It will be something like this one. You can see that entropy has increased, pressure has dropped, and you have gone back to the initial state. This one was 0.1. And then comes the evaporator, which is at constant pressure, and then you go back to 1. This is the simple vapor compression refrigeration cycle. Okay, and this part is that QE, and we mostly call it as QL because you can see that it works at negative 20 degrees Celsius here, and therefore this part it is Q high, or it is called Q out. It is at high temperature because you can see the temperature value here, and you can see the temperature value here. Okay. Now, similarly, we can draw it in pH diagram, which is the pressure versus enthalpy diagram here. So that pressure versus enthalpy diagram, I will do the similar stuff here, and then you will have that low pressure. Let me just write it. P low is 140 kilopascal, and the P high is that 720. So try to find. So 140. So 100 is there, and 1000 is there. Is 1.4. It is approximately here. So I'll just start with the 0.1, and then you will have that 720 kilopascal. So you will have that. You will have that 2, 3, 4, 5, 6, 7. You will have that 7 here and 8 here. It will be approximately at this range. This is the next 720 here, and 100, 200, and then you will have that 120. Okay, sorry, 140. These are approximate values, it doesn't matter at the end. 140 kilopascal. Okay, so with this in mind, now let's draw the pH diagram, but you have to notice that this pH diagram, it is all about the, so you have also this constant entropy lines. You will go from P1 to P2, it should be isentropic. So you can see that S is 1 here, and you have to be parallel to these lines. It should be isentropic. Let me just do that. So I will go to the line here. It is that line. Let me just check it. So that, yes. Okay, so it will be that point 2. So that 1 to 2, it is isentropic compressor. And then from that 2 to 3, you will have that isobaric condenser. Let me just do that here. And you will have at the saturated liquid state. This 3, this 1 to 2. Okay, you can see the pressure is constant. And then 3 to 4, you will have that isenthalpic. You have that thermal expansion valve. It should be isenthalpic, so you have to go downwards till the initial pressure value here. And see the initial pressure value. This is it the same? It is approximately the same. Just let me give a space here. So you will have this one will be at 4. So isenthalpic, you can see the enthalpy is constant and the expansion valve, the pressure drops. And then you have the 4 to 1 here, which is that isobaric evaporator. Okay. For this isobaric evaporator, you will have this Q in. That one here, and that's the direction. Here you will have that Q in or Q low, as I said it. Here you will have that QH or Q out. Okay. This is how the pH diagram works for the compressor. So it's a vapor compression cycle. Okay, that next comes the energy units. We also have the COP here. Let me just give the definition of COP. That firstly, let me just write with the evaporator here. So Q in. Q in of the evaporator is H4, H1 minus H4. This is for evaporator. The enthalpy at 1 minus enthalpy at 4. You have to always have the positive value. Therefore, you take the higher enthalpy value. So Q out, which is the condenser, it will be that H2 minus H3. Because here the 2 is more than 3 because you have this Q out. And then work in should be that H2 minus H1. This is for the work in. Okay. And as well as you will have this COP, which is the coefficient of performance, and it is like the efficiency. And what you are doing is that you are dividing the refrigeration capacity, which is measured by Q in here, with working. This is the COP value. And COP value, it is approximately 3 to 3 for the, can change, okay, so that for the real refrigeration cycles, it's about 3. At the end, you should remember that COP is greater than 1. It is greater than 1. It measures the capacity or the efficiency of the refrigeration cycles. It can be 7, it can be 8, but for the industrial refrigeration systems, it's about 3 to 4. Good. Let me see if I've said all of the things here. Okay. And this ones I should add that is refrigeration. Okay, now let's go back to here. So that we have one unit which is COP. This one is dimensionless, but this also we are using that EER. So that EER is that 3.41 times COP. And also we are using that 1 ton here, and 1 ton of Q in. Q in is that QL, or it is cooling capacity. Okay. And for this Q in, 1 ton means that you will have that 12,000, you will have BTU by hour, or 3616 watts. Okay. So this is the 1 ton of cooling capacity. Okay, this is also used for the refrigeration cycles, and the BTU here means that British thermal unit. It's 10 to the 5, so it will be 10 to the 5 joules. It's energy unit. And then let me just see if I have all the terms here. Okay, and one more thing here is that I should tell you, this evaporator part here, it takes Q in, therefore it cools. Okay, therefore, and for refrigerations, we take this part. But if it is heat pump, the heat pump is that you are heating the system. So if it is refrigeration, so it means that your aim is Q in or QL. If it is heat pump, these are the same components, okay, the same components. Our aim is Q out or QH. So if it is heat pump, this is the part that is inside the room, for example, inside the office building. This is the part that is inside. If it is the refrigeration, this is the part that is inside the room. So if you want to cool the room, for example, in summer, then it will be that it is refrigeration. If you are trying to heat the room, for example, in winter, then it means that it will be heat pump. At the end, they are the same components, but the name is different. Okay, good. And one more thing about the compressor is the volumetric efficiency. This is also another important concept used for the that is for compressor. For similarity, I will just want to give you one example here. For the volumetric efficiency, it will be our heart. Okay. So that our heart has some volume. Okay, it has some volume here, and then so that you have the contraction and the expansion here in our heart, so compression and expansion. So it displaces some volume, and this volume is geometric. Okay, if the room is very hot, okay, for the very hot room, what happens is that the body needs cooling. So our body, so it needs cooling. So how do we do this cooling? You can do this cooling by sweating, or you can supply more blood to the skin. So therefore, what you need is that you will need more blood. And how to supply by more blood? So it means that the heart, so you should have some more beats. It can be that this beats is, for example, 140 beats per minute. The heart increases the beats to 140. So the problem here is that the speed of the heart is very high, and it has some volume, so that there is not enough time for the blood to fill all of the heart. So here you will have that, the drop in volumetric efficiency. I will write it, drop in that volumetric efficiency. I just write the eta volume, and I will explain what happens here. Eta volume here. The drop in the volumetric efficiency. Why there is a drop? Because that speed is very high. So let me just erase that part. The heart speed is very high, and it doesn't allow so that not enough time that for the blood to fill in heart. There is not enough time for the blood to fill in the heart. So the heart opens and contracts so fast that sometimes it is empty. Okay, empty heart means that that you are wasting energy. So it means that waste energy. Therefore, that after some time, you can exhaust the body and the people can die. The person can die. So that is the dangerous side of the very hot room. Similar thing happens in the compressor. Let me just give you the compressor here. So for the compressor, so if it is a piston cylinder device here, Say that this is the compressor and you have some inlet and you have some outlet and you have some piston here. Okay, and this piston moves between, let me just draw the lower part of it too. Okay. Here we'll have this piston. This is the top dead center and this is the bottom dead center. This piston displaces this amount of the volume here. This is the volume that it displaces. This is the volume displaced, and this is geometry. So you design it. But when the compressor displaces this volume, and you have also the inlet for that compressor, and that inlet is the volume of the refrigerant. Okay, and this one is called also that V suction. Okay, the suction head of the refrigerant, volume of the refrigerant, is not the same as the displaced volume here. So say that the displaced volume of the compressor is 1 meter cubes, but the suction will be 0.8 meter cubes. It will be less than that one. So that V suction, it will be less than V displaced. At the maximum case, it will be equal for the ideal case. Okay, but for the reality, it will be less than that one. Why it is less? So I will look for the cases for that one, but the simplest case is that you will have the pressure losses, and that pressure losses, then you will have the drop in the volume of the refrigerant that enters the system. And it also depends on the, that density of the refrigerant at inlet. Let me just show it to you. So you can also write this one as V dot. If you divide both sides by time, V dot of the suction head will be less than V dot of the displaced. Okay, so this is the volumetric efficiency, and I will just write the suction flow rate. It will be that equal to that m dot of the refrigerant and divide by rho inlet, because at inlet here you will have that density of the refrigerant. So rho inlet, that is the density of the refrigerant, and for this density of the refrigerant you can just write so that P by RT, and these are saturation values, because if you remember from our previous slides, we have said that inlet is at quality of 1. So it is saturation temperature and the pressure. Okay. So that for this one, what you are doing is that this is approximately, not exactly, approximately, and you are assuming that it is ideal gas. Okay. So therefore, what you see here is that for the eta, volumetric efficiency, that is equal to, so that V dot suction and V dot displaced. This displaced volume, it is geometric constant. You can't change it. You cannot change it. It is constant. This one is constant. So what it means is that if this one drops, the efficiency drops. The volumetric efficiency drops for a constant m dot of the refrigerant. If you have a constant m dot of the refrigerant, so it means that if the rho inlet increases, this one will drop and the efficiency will drop. So rho inlet increases, then suction flow rate drops, okay, and then so volumetric efficiency drops. That is the case for the refrigerant here. And as you can notice that if the temperature increases, the P saturation also increases, but it's an exponential manner. And therefore, at the higher temperatures, you have the drop in volumetric efficiency. That is the case for the piston cylinder device here. Okay. But you have to remember that this one is only for constant mass flow rate. Okay. And you can also analyze for this one for a given volumetric efficiency and as well as for a given mass flow rate for different refrigerants. So now this is another graph here that's again for the volumetric efficiency. Now what I will do is that I will just write the previous formula here. It will be that, so suction flow rate and divide by displaced flow rate. Okay. And for that suction flow rate, you can just write as that m dot of the refrigerant divided by the rho inlet. Okay. And the rho at inlet, I'll just write the same formula as I've written before, P saturation by RT saturation. Okay. Now, I will take a different approach here and say that, so that eta volumetric is given, it is 0.8. This one is given, and the constant. And I know that the V dot displaced, it is the geometry of the compressor, and it is also fixed. But it means that only this one can change, V dot suction. So that V dot suction can change. Or the rho inlet can change. Sorry, that V dot suction is constant. It doesn't change because volumetric efficiency is constant. So here you will have that. Let me just write it. So that m dot will be equal to, so that V dot suction, and it will be multiplied with the rho inlet, and I will just write that P saturation and divide by RT saturation. And this one is also constant because that volumetric efficiency is constant. This one is constant. Therefore, this one will be constant too. So m dot mass flow rate can increase or decrease depending on the saturation pressure and the saturation temperature. Okay, now let's see the chart as in the previous case here. We can see that small increase in, so that, for example, if the saturation temperature rises from 25 degrees Celsius to 150 degrees Celsius, a temperature change in this amount, but the pressure change is very huge. So you can see that it is 500 kilopascal. A huge pressure change with respect to small temperature change. Okay, so Psat changes faster than the Tsat. Okay. So what it means is that if I increase the saturation temperature here, so if I increase it, since this one change increases faster than that one, the mass flow rate will increase. Okay. So increase T saturation and the P saturation, it goes up faster. Okay. And therefore, what you will have is that mass m dot increases. Okay. Because this one is in the downstairs, this one is in upstairs. This one increases faster than that one, therefore the total combination will increase. Okay. So since P sat by RT sat, okay, will increase. It's like a competition. This one increases faster than that one, therefore total combination will increase. And therefore mass flow rate increases. And therefore, if I increase the saturation temperature at inlet, you can see that cooling capacity. This is the cooling capacity, it increases. Why it increases? Because that cooling capacity is proportional to mass flow rate of refrigerant. It is proportional to mass flow rate of the refrigerant. Therefore, if I increase the saturation temperature, the mass flow rate increases, and as a result, the evaporation part of the flow heat transfer increases, and this is the cooling capacity that we have, and it also increases, and it increases very fast due to this P saturation increase faster than the T saturation temperature here. Similarly, the Carnot efficiency and the real efficiency also increases. Okay, this is the first part, and here I've written this one as a TL, because that if I go back to the chart here, here, T1 saturation is same as T4. And so this is first low temperature part. Okay. And T1 is same as T4, and that is TL. Similarly here, T3 is T high. This one is the high temperature, which is at 30 degrees Celsius. This one is T high, which is 30 degrees Celsius, and this one is negative 20 degrees Celsius. Okay. This is another thing that we should consider in the refrigeration systems, and therefore refrigeration is better when that temperature is higher at the compressor inlet. Now comes, how do we select the refrigerant? What are the things that we should consider while selecting the refrigerant? You can see there is a different list of the refrigerants. You can see R11, ammonia, isobutane, so that R12. So even water is a refrigerant, carbon dioxide. And what is the thing that we should consider and when we select the refrigerant? First thing that I will start with, that is the COP value. You can see it is maximum for R11 and drops the minimum value for carbon dioxide. And what we are doing is that we are working between 0 degrees Celsius and 30 degrees Celsius. And the 0 degrees Celsius, as I said, it is the minimum part of it. You can see this part is the 0, and this part is that 30 degrees Celsius, which is the maximum part. Okay. For the COP value, this one is highest. But another thing here is that Q in. Okay, this one is that QH, which is Q out, and the QL is Q in. So QL is cooling, and the QH is heating. So you should have this QL value as high as possible for the cooling capacity. You can see for water it is the maximum, for the ammonia it is also higher, but for other ones it is small. Okay, and this QH is also for if you want heating, it should be also very large. Okay. And this QL and the QH, both of them are depends on the change of enthalpy during vaporization. Because this, if you go back to here, during QL and the QH, you have phase change. QL and the QH, it means that it is phase change. Okay. And in phase change, what we are interested in is that enthalpy of vaporization. So in other words, HFG or Hg minus HF. That is the enthalpy of refrigeration. And this enthalpy change during phase change, it should be very large. It should be very large so that QL is high, so that QH is high. Therefore, that is another thing that we should consider. For water, you can see it is very high. For this one, it is high. Ammonia, it is also high. For other refrigerants, you can compare the values. And the one more important stuff here is that, so that inlet row, this is also important. And let me just show it to you again. So if you remember, we have said that the suction head was equal to that mass flow rate of the refrigerant divided by the raw inlet. Okay. And the inlet density for a given mass flow rate. Okay. So what we want is that we want that we can look at this without suction. Okay. If the density is very low, you can see for water it is very low. This one is very high. So this one becomes high for low density. Okay. If this one is high, so what we want at the end is that volumetric efficiency. If you remember, it was that V dot suction and divided by V dot displaced. If the suction flow rate is high, then if you want higher efficiency, this one should be high too. Because this one is high and this one should be high. So if it is high, it means that you need larger compressor. Okay. And the larger compressor means that it is weight and it is cost. And see, so these two things add complexity to the problem. And therefore, the best thing is that you should have the higher density. So that, let me just add these ones as a comment here. These two, so these three values here should be high. Okay, and also this density value here should be high. Okay, good. Now work in that is required for the compressor here, it should be low. Is desired. Okay, now comes that critical part and the triple part. I will talk about this one. And also next one is that the high pressure and the low pressure. Now let's see that one. PL. So PL, it happens in evaporator. Evaporator has the lowest pressure. And the P high, it happens in condenser. Okay. Now let's see the first, the evaporator case. For the evaporator, here you have the low pressure and here you have the 180. Okay. If it is very low pressure, so that pressure can be very low, such that you have the leakage. So for very low PL. This one is also not desirable. For example, for water, you can see that the low pressure it is very, very low. So this one means that so that you can have leakage. So to prevent leakage, you have to have the that thicker walls and the complex structure that it doesn't allow any leakage problem here. And if the pressure is high, so let's see the condenser case now. So here you have the P high, and here you have the 180. Okay, so you have the pressure difference between inlet of the between inside the condenser and the environment. And for this high pressure difference, again the walls here, so structure should be that powerful enough so that there is no any damage happens inside the system. If you compare the P high values, see the highest value happens in, for example, this one. You can see these are very high, they're not desirable. Good. So I've talked about this one, and also the CP value, that coefficient and the specific heat value. This CP value, it should be high. Okay. And why it should be high? Because if it is very high, it means that the temperature will not change if it accepts lots of heat. For example, for water, okay, this one is used as in chillers. Okay, what do we use in chillers is that the water has very high specific heat value, and therefore if it changes the temperature of the room, for example from 25 degrees to 40 degrees Celsius, its temperature doesn't change enough. And if its temperature doesn't change enough, so that it means that we don't need much cooling for water here. Okay, therefore this CP value should be very high, such that we have the good heat transfer without any significant temperature change in the working fluid. Okay, this is another stuff here, and now comes the last part here. That last part will be that the triple point and the critical point. Okay, now let's see that one. So that critical point is here. So triple point. Triple point is end of this phase change part, because here you have the liquid vapor. Okay, and the triple point, critical point is the other extreme, and the triple point is another extreme here. Okay, so let me just draw it for you. This is the vapor dome, and you have the maximum point as the critical one, and you have the minimum as the triple one. So you are working between these three extremes, and the critical should be as high as possible, and this one should be as low as possible, such that, because if you remember, we have two pressure ranges. One is that P high, and the other one is P low. Okay, so these two values, these two extremes, should be so large so that we can work, that safely. For example, if it is very, that if the triple point is very high, okay, if it is very high, it means that so PL, as well as you have the TL here, and P high, you have the T high here. If the triple point is very high, then it means that you cannot work at this range, and if you can't work at this range, it means that TL should be very high. So that, let me just summarize what I'm trying to say, is that TL should be greater than T triple, and the T high should be less than T critical. Okay, actually this one should be that case. Okay, and they say that the critical temperature is, let me just give you one example, 0 degrees Celsius. It is water, so that this is triple. The triple temperature for water is 0 degrees Celsius. So what it means is that if you have refrigeration that uses the water as refrigerant, that one cannot cool the system to 0 degrees Celsius. It should be above it, because at lower temperature, that the cooling capacity should be higher than the triple point. Opposite thing happens if, say, that the T high, if this one is, for example, it's about 25 degrees Celsius, T high. So that sorry, it's not the T high, so I'm mixing the terms here. It should be T critical. Okay. If the critical temperature is 25 degrees Celsius, if it is 25 degrees Celsius, what it means is that T high, so that heating of air conditioner, for example, it can't be more than 25 degrees Celsius. Okay, so you have two extreme values. Triple point should be as low as possible, and this one should be as high as possible. So this one, you have to have this higher. High is desirable here, and for the triple point, low is desirable. Okay. For water, you can see that this is not good. 0.025, 0.01. For water, it is okay, but for other refrigerants, for example, for carbon dioxide, it is not good. Okay. And another stuff that we should consider for selection of the refrigerant is that the toxicity, if it is toxic or not. For example, ammonia is toxic. And the flammability and the ozone depletion, and for example, some refrigerant, for example, R134A. It is a very stable refrigerant such that it can rise to the very high parts of the atmosphere. And in that high parts of the atmosphere, it can react with the ozone layer and deplete it. And the global warming is also important. For example, CO2, it has a global warming effect. Okay. And there's a naming convention for the refrigerants when we have the RXYZ here, and the X means that carbon atoms -1 and the hydrogen atoms +1, and the Z means that number of fluorine atoms. For example, if you have that R22, it is same as R022. It means that you have so X is, let me just write it here. So you have one carbon atom, and it is 2. 2 means that it is hydrogen atom +1, so you have one hydrogen atom. I have that 2 here, and 2 is that 2 fluorine atoms. Okay, so you can see that one carbon atom and one hydrogen and 2 fluorine. So a carbon can create 4 bonds, so that one bond will be with hydrogen and other 2 bonds will be with fluorine. And one bond is not there, so it means that it should be chlorine here. So there is chlorine, there is hydrogen and the fluorine. Okay, therefore these are called as HCFC. Okay, so that hydrogen, chlorine, fluorine, and the carbon. Okay, and there is also that CFC and the CFC. So sorry, HFC and the CFC. Okay, it is also possible that you can have CFC and you can have that HFC, etc. Okay. Good. And now comes the refrigerator with a freezer part, and now let's draw the TS diagram for this one. For the refrigerator with a freezer, let me just write the components here. Again, we will have the compressor here, compressor 1. You have inlet, which is 1. You have outlet, which is 2. And from that one, you are going to condenser, and you have that 3 here. From that condenser, you will have that thermal expansion valve TXV, and you will have that 4. Then you will have the evaporator here, and you will have this one as 5. And this is one cooling part, so this is cooling part 1. Okay. And if you want more cooling, what you are doing is that you are adding one more TXV here, and this one is 6, and you will have that freezer here, and it goes back to this compressor here. Just draw it again. So you will have this freezer, and then this one is 1. Okay, you can see that here you have much lower temperatures with adding this second TXV, TXV2, and this one is TXV1. If I just write the pressure values here, P2 is greater than P1, and then P3 is same as P2, and the P4 is less than P3, and the P5 is same as P4, and the P6 is less than P5. Okay? And then P1 is same as P6. So that P1 is that P minimum. You will have that P6 not P6, it will be that P5. It will be in medium range, and then P3 or P2, it will be the Pmax. Okay. Now let's draw it on a TS diagram here. And to draw it as a TS diagram, what I will do is that here you can see that there are 3 isobaric lines. Okay.